All right, so you will need a text editor for your normal text editing. I recommend VS Code, but it's up to you to use whatever you like. Um, there's actually a much more sophisticated environment called PyCharm, and there's a community version for it. It's sufficiently sophisticated that you probably won't have to learn how to use it fully throughout this class, right? So I would like you not to be hampered by the complexity of the environment, but if you want to become or have to deal with Python in the long term and want to become developers, then it's probably better that you try that or try something that is a bit more sophisticated in terms of ability to understand your code and highlight potential bugs and help you with testing and so on, right? Because what we're going to do with VS Code, with Visual Studio Code, is very basic. All right, we're going to run. So let me know a little bit about your backgrounds. How many of you have computing backgrounds? 1, 2. Math? 3. Math? Okay, a few more. So the rest of you, where do you come from? What kind of majors do you have or intend to have? Psychology, how many of you? Nobody. I would have like half the class students from psychology. So humanities in general? How many of you are humanities? How many of you are other sciences, like physics and chemistry and... Okay, thank you. So the rest are from where? Because half of you have not raised your hand yet. Louder, please. Economics. How many of you are from economics? Okay, quite a few. What else is there? Business. Law. Do you have a law school? So, for instance, where are you from? No, next to you. Oh, so why didn't you raise your hand? Because I only took like one class. But that doesn't matter, right? So it means that I can push you harder, right? I can have the expectation that you would want to work harder for this class, right? So it doesn't matter how much experience you have in computing. If you have a computing major, right, you should raise your hand. So actually, how many of you are computing students? Okay, it's like maybe a third of the class. Cool. So let's start with our first pieces of code. Okay, I'm going to make the font a little bit smaller. So we're going to have two ways of running code. And I'm going to start today with the easiest, which is idle, using the integrated environment for that comes with Python. So it's called idle, and opens a prompt that is very similar to the prompt that you see on the command line, right? So this is the prompt that you see on the command line, and what happens is that I have many versions of Python here, right? So as I run them, I don't get the same version, but it doesn't matter, right? So you see this one, which is running in a terminal, is very similar to this. The difference is that when I press Ctrl D here, idle terminates. And when I press Ctrl D here, the terminal stays on and I can restart, right? And this will change the way we work with files. We're going to prefer to work in the terminal and create new files via VS Code. But we're not going to do this tonight because we want to get the look and feel of Python. So I'm going to start idle again. In principle, idle allows saving files. All right, so we can save files, but it doesn't save actual Python Python files. Actually, I can open a new file here, right? Seems so. I've never tried this. Cool. So we have an interactive environment. What we call this is a REPL. REPL is sorry. I actually can't remember what the so it's repeat eval print read eval print loop, right? Read eval print loop. So it reads a piece of input, it evaluates it, it prints the result, and it repeats that. So if, for instance, I type something like 2 plus 3, right? 2 plus 3 is the input, is the read part, right? It gets evaluated internally. That's the part that we don't see. And then we see the print, which is 5. And then we can go again, and we can repeat it forever, right? So this is a class of languages. There are quite a few that work in that way. There are quite a few that don't. For instance, Java doesn't have a REPL. Java, C, C++, Golang, and so on. There are many of them that don't. In general, languages that do have such a REPL are considered easier to learn because the feedback loop is faster. You can just type something and get immediately see what happens. Whereas with writing a Java program, you have to complete that entire file. You have to save it. You have to compile it, right? So there's a good maybe 30 seconds between you writing your code and seeing how it performs. But the advantage with those languages are that for very large programs, for very large pieces of code, they are a lot faster. And they consume fewer resources internally, less memory, given the amount of data that they need to process. Right. However, for very small programs, Python seems to have a faster interaction loop, and therefore it leads to faster learning. So the first thing we see is that Python is an expression-based language. We can type any kind of expression, as complicated as you may want to make it. Right? And it prints the result. All right? Now, if it only did that, it wouldn't be a very useful tool, right? So we're going to try to learn how to define computations that we name, right? We're going to try to define functions. The first function that we define is one that is very simple. Let's define a function that squares. Square a number x, and the result is x times x. All right, so you see as you input the, I'm going to repeat this. Right, so I press enter, and I don't get a prompt immediately. Right, so the prompt waits there. Maybe I have some more stuff to type inside the same function. And only when I press enter again, does the interpreter figure out that, oh, this is the end of the procedure or the function that I want to do, and it allows me to have the prompt back. So now if I say square 10, I'm going to get the result, right? So how do we define a function? We give it a name. Pretty much like in mathematics, we have a list of arguments. In this case, there's only one. We put a colon here. This environment is not very good at selection. So we put a colon, right? And then we use this keyword return. We want to tell Python what to return as a result. And we want to return the result of this expression where x is whatever it gets passed in as an argument, right? So whenever we say square of some number, right, that the result will be returned. Okay, so we can do things that are a bit more complicated. For instance, the distance between or the length of a vector placed from origin to coordinates x and y would be, so let's call this dist, right? Dist from origin. So we would have a def because we're defining a new function, and dist, and we would have two arguments x and y, and we would say that we're returning, and we would like to have a function for the square root. And that function, you might expect it to be called sqrt, right? X, and I'm going to say square. I'm going to reuse the previous one, square x plus square y. And let's see what happens, right? So the definition is currently accepted. And if I say dist of 10 and 20, I'm going to get an error saying that this name is not actually defined. We have an expectation that a square root function will be called sqrt, but we just guessed, right? Now, what happens is that Python doesn't load all its code at once, right? Part of it is still on the hard drive because you want to save memory. While it runs, you want to save memory, and you want to load only as much as it is necessary to run the computation at hand. And in order to load those parts that we might need for our computation, we use a directive called import. So I'm going to say import math. Okay, and you see that the math object, the math library, the math code set is being loaded into memory, right? There's no error, so it means that must have worked. And math is actually a module. And one thing we can do with any Python entity is find out what's inside and ask for help. So I can say help math, and I'm going to get some help. And this help is a bit long. And this window doesn't allow me to scroll. How do I scroll here? That's very annoying. So this is a very long. Okay. This is a very long piece of text that will tell me a bit of help and will give me an idea of what's inside. All right, and you see a bunch of names that seem familiar, right? ACOS, right? ARCOS, arcsine, ceiling, cosine, degrees, right? Exponential. There's the exponential here, right? The exponential function here. And if I keep scrolling, you see, maybe you have seen sqrt. Okay, here it is. Right? So there's the sqrt function. We can also be a bit more less verbose, right? More concise, and say dir of math, which will only provide the content without the help text. Okay, and now we want the sqrt name to become available. So I'm going to say from math import sqrt, and now the name sqrt becomes available. If I say sqrt of the value 2, I will get the square root of 2, right? So at this point, our distance function works. This thing doesn't let me repeat the history. Okay, I can't repeat the history. I could repeat the history though, just no, control. Okay, so we go back to dist of 10 and 20. And now we see the result. Okay, cool. So we have learned how to define functions. Okay, so let's try to define something more interesting, right? Have you heard of the Fibonacci sequence? What is the Fibonacci sequence? Very good, right? So we can start with the first two numbers. Very frequently they are 1 and 1, right? But we can also start from 0 and 1. I'll tell you why, because in computing, we often start counting from 0. So what you see as the first element is the 0th element, right? The element rank 0. And it's just nice if you say that the first Fibonacci number, the 0th Fibonacci number is 0, right? And then the first one is 1, the second one is 1, and so on, right? So every Fibonacci number after the first two is the sum of the previous two. 5, 8, and so on, right? So do you know how it originated, where it comes from? Nature, but more precisely. No. It's true that it is related to sunflowers. So sunflowers, the spiral of the seeds has something to do with the Fibonacci sequence, but no. So who is Fibonacci? Leonardo Pisano. He was nicknamed Fibonacci, right? So he was the person who solved the problem, right? The problem was the following: if I have a pair of rabbits, right, just newborn rabbits, and it takes 1 month till the rabbits are mature enough to breed, how many pairs of rabbits will I have over n months, right? So obviously, the first pair of rabbits is here, is this one, right? Let me push this a little bit higher, right? It takes 1 month. After 1 month, they have just grown up to the point of maturity. So I still have 1 pair of rabbits, but they can breed now, right? So 1 pair of rabbits breeds another pair of rabbits. So after 1 month, we have 2. But only 1 of the pairs is mature enough to be able to breed, right? So that pair breeds again, right? So we have 2 pairs, but this one is able to breed, this one is not, right? So as you move forward, this one is able to breed 1 more. So we're going to have 3 pairs of rabbits, right? But at the point where we have 3 pairs of rabbits, actually we have 2 of them that are capable of breeding. So 2 of them will add 2 more pairs, so we're going to move them to 5. So at every month, right, let's say we're here, the number of pairs that are capable to breed is this number, which is just the preceding one. They existed there, and it takes 1 month for the pairs to mature, so they will get here, right? So what did Fibonacci really solve? He got an analytical formula for this series, right? So he discovered that any Fibonacci number, Fibonacci n, is 1 plus square root of 5 divided by 2 all to the power of n plus 1 minus square root of 5 divided by 2 all to the power of n. But the second one is a number that is less than 1. So because it's to the power of n, it very quickly becomes very small. So it becomes negligible. So pretty much the Fibonacci numbers are 1 plus square root of 5 divided by 2 all to the power of n. you round to the closest integer, right? And that number, 1 plus square root of 5 divided by 2, is called the golden ratio. Very good. The proof is very interesting. How do you get there? But this is not what we're trying to do today. So let's write a piece of program that computes the series. Or better said, not the series, but I want to find out the nth Fibonacci number. All right? So def fib, we tend to abbreviate everything, right? And we want the nth, right? And we're going to start counting from 0. So we're going to say that if, so we're going to return a value, right? And that value is return, and we return n if n is less or equal to 1. Else, we return fib n minus 1 plus fib n minus 2. Does this make sense? So we're introducing a new construct. And if you remember in math, how do you define sometimes a function? You say, well, this function of some argument x is equal, and you draw a big brace. And you say, oh, it has this expression if something is true, and you have this other expression otherwise, right? Remember this kind of definitions in mathematics? Yes? So it's a case-by-case definition of a function. So we're doing the same thing here, right? So we have this Boolean, right? Logical expression, an expression that is either true or false, and can be either greater or equal to 0 or less than, less than or equal to 1 or greater than, right? So n less than or equal to 1 is either true or it isn't. If it is true, we return n, which is, what are the possible values of n when n is less than or equal to 1, assuming that n is an integer and it's a positive integer. We're not interested in negative integers for the time being. Only 0 or 1, right? So if n is less than or equal to 1, we return n. So when n is 0, we return 0. When n is 1, we return 1, right? So the 0th Fibonacci number is 0. The first Fibonacci number is 1. So this is conformant with the definition. Otherwise, we return the sum of the previous two numbers, right, in the series. But the previous two numbers are fib n minus 1 and fib n minus 2, right? So their sum would be my result. So this expression, if I could select properly, it would be absolutely fantastic. For some reason, it's idle, that doesn't work properly. So this expression has a value, right? And let me show you that this happens. Let's say n is let's just write something, right? So if I want the value of 10 if 3 greater than 4, else 20, right? So 3 greater than 4 is false. We're going to get as a result, we're going to get 20. This thing has value, right? And has the value 20. So how is it computed? First, we look at this logical expression, right? This expression here is something that is either true or false. If it is true, we're going to return what is before the if. If it is false, we're going to return what is after the else, right? So that thing has a value all the time. It's a very nice way of building up results. Now, what we have here is similar, just that we are using the name n to denote the argument of f. And then, once that is computed, we can use the return directive to tell Python to return a result from our function fib. Yes? So fib n is and if n is less than or equal to 1, else fib n minus 1 plus fib n minus 2. And this return tells the procedure, the definition, the function what it is. So now if I'm going to run fib 0, I'm going to get 0, fib 1, I'm going to get 1, fib 2, I'm going to get 1, fib 3, I'm going to get 2, fib 4, I'm going to get 3, fib 5, I'm going to get 5, fib 6, 8, fib 7, 13, fib 8, 21, and so on, right? Is this definition clear for everybody? So this is the definition of Fibonacci. Cool? How about factorial? Can we write a function that computes the factorial? Factorial of a number n. So I'm going to have three parts, right? I'm going to have something if some logical expression, else something else. What should be the logical expression here? Are you sure you want to say greater than 0? Okay, then what do I put here? So that's a possibility. He said n greater than 0. I'm curious what he's going to say. What do I put here? Okay, so n equals 0, say sum. So notice that equality is double equal. The test for equality is double equal. We're going to see why later. Just remember it for the time being. What do I put here? 1. Good. Else? Louder. N times what? Louder. Fact n minus 1, yes. Very good. I can't just multiply with n minus 1. I'm just going to get 3 times 2, right? So this would be a good definition, right? If I say factorial of 1, I'm going to get 1. Factorial of 0, I'm going to get 1. Factorial of 2, 2. Factorial of 10, it's 3 million something. What if I say factorial of 1? Let's not make it 1,500. I think happens. Gives a big number. Very good, right? So that's a very nice aspect of Python, right? And by contrast, let me show you. So I'm going to do the same in JavaScript. Okay, I'm going to say fact equals function n return 1. So this one works a little bit. N equals 0, n 1 or n times factorial n minus 1. All right, so fact of 1 is 1, fact of 10 is fact of 500, right? It's not infinity, right? It's this number. Just that Java doesn't have the level of precision to deal with such big numbers, right? Most of the languages do not have Python's ability to work with large numbers. Now we're gonna learn very quickly. I'm gonna try 1000 here, and you're gonna see an error, and we're gonna learn why this error occurs, and it's possible to get rid of it, right? So don't worry too much about it. If I want to really compute factorial 1000, it's possible easily in Python, right? Now, notice the fact that all our functions, in the definition, they mention themselves. So factorial here is also mentioned inside, right? And the same happened with Fibonacci, right? So what do you think? Is this a chicken and egg problem? You know the chicken and egg problem? You know what it is? Everybody knows, right? What was first, the chicken or the egg? What do you answer to that? Good answer. Good answer. All right. So it doesn't really lead to a chicken and egg problem, right? Because, well, if I want to compute factorial of, let's take factorial because it's a simpler computation, right? So let's say I want to compute factorial of 3. I don't want to take a too big number because I don't want to write too much by hand. So factorial of 3, it looks at the definition and it says, oh, 3 is not equal to 0, right? So I'm going to pick the right side, right, the one after the else. So I'm going to replace this entire expression by 3 times factorial of 2. And this we can't evaluate right away, right? We have to sort of, the 3 star part, we have to postpone and wait for a little bit until this one, factorial of 2, gets evaluated, right? We have to evaluate factorial of 2 first, and then we can evaluate the whole thing. Now, factorial of 2, it goes again to the definition and says, well, what's the definition of factorial? Well, 2 is less than, not equal to 0, so it should be 2 times factorial of 1, right? 2 times factorial of 1. But computers are stupid. So they will see that 2 times factorial of 1 is an immediate replacement for the factorial of 2, and they will associate the operations in this way. And because of that, they can still not, they will not go and say, oh, let me collapse 3 times 2 into 6. It would be good if they could do that, but they can't, right? And then we reach factorial of 1. And again, go to definition, say 1 is not equal to 0. So this is going to be 1 times factorial of 0, right? And finally, it goes to factorial of 0 and sees that, oh, 0 is equal to 0, so the result should be 1. So it goes and replaces this by 1. And now it can compute 1 times 1 is 1, times 2 is 2, times 3 is 6. Okay? So you don't have a chicken and egg problem. You always hit the base case. There is one case there that doesn't require a recursive reference in order to enable the computation, right? And this is why recursion works. Whenever we have these kind of definitions where the function that is being defined refers to itself inside, this is called recursion. Those are recursive functions. But there's always at least one case inside that can be resolved without a recursive reference, right? In the case of factorial is n equals 0, right? In the case of Fibonacci, both n equals 0 and n equals 1 do not need recursive references, okay? This is something that should be very familiar to you from mathematics. So when you define factorial in mathematics, the definition looked like this. N factorial is defined as n times n minus 1 factorial if n is greater than 0, and 1 if n is equal to 0, right? Wasn't that the definition? So your math teacher, without telling you, taught you about recursion. This is a reference to what is being defined, which is this thing, right? So recursion actually should not be foreign to you. Defining functions recursively is generally more mathematical, and what I've seen is easier to learn because it looks at relationships between entities and it doesn't look at sequence of steps that need to be performed. Thinking in sequences of steps that need to be performed is generally more difficult. Okay? All right, so let's go back to the definition that we had. So we had definition of factorial and somebody said if n greater than 0, else. Can we make this work? Can we find something to put here and something to put here so that the definition works? Just flip it, yes? So I can say it's n times factorial of n minus 1 if n is greater than 0, else 1. It's equally good. It's going to work, right? Factorial of 10 is going to produce the same value. Okay. Now, there's another important concept that comes when we talk about functions. All right, and I'm going to try to introduce it now, and it's going to require a little bit more ability to abstract. So, you all know numbers very well, right? Or you think you know numbers very well. So if I say what is 3, you know what is 3, right? But if I asked you to point at 3, you can't, right? 3 is an abstract concept. You can point at 3 people, you can point at 3 apples, you can point, right? So imagine how the concept arose. At some point, somebody realized that the fact that you have a group of 3 people and 3 apples and 3 oranges, they all have a common property. They have something in common, and that property should be called something, right? And then if you put one more person in the group of persons and one more apple in the group of apples and one more orange in the group of oranges, then you have preserved that property of the 3 groups having sort of, right? And the property is simple. You have a bijection between any 2 groups. Okay, so that concept sort of evolved, and you have learned it at a very early age, and it's been so long you don't even worry about it, right? You think that, oh yeah, I know numbers, I know what 3 is. Okay, one important thing is that numbers are nameless. They stand for themselves. 3 stands for 3. So if I go in mathematics, I don't have to define a variable, or I don't have to give a name to number 3. I just write 3. But very frequently, we have to give a name to a function. So for instance, the function that increments its argument by 1, right, adds 1 to its argument and returns the result, we have to call it something. We have to say that, oh, that's F or G. We call it something, right? We give it a name. So we sort of got used to giving names to functions, right? And we don't realize that there's a disparity, that because of that, functions are a little bit more less privileged than numbers, right? For functions, we don't have a language that allows them to stand for themselves and express their own computation, right? We have to give them names. And we have done that so far. We have defined a function that we call Fibonacci and another function that we call, factorial, right? And a function that was called square, and so on, right? We don't have a way to say, oh, there's an expression that represents a function, but we haven't given it a name, as we have for numbers. Okay? It's very important. right? So having equality between all entities inside the programming language is extremely important. Later, we're going to learn about strings, and we're going to find out that, oh, strings can stand for themselves as well. I don't have to give names to strings. The string classroom, I just put it in quotes, and this is the string classroom. I don't have to name it something else. Okay? So by the way, we're going to learn soon to name things. I can say x equals 3, right? And x from this point on is 3. And but I don't have to. 3 is 3. But the function square, so more importantly, the function Fibonacci, right? We can't define it without naming it, right? So fib, for instance, if I just use the symbol, you're going to see that underlying it, there's an entity, but we don't have a language for it. So there's a notation that allows me to do this, define functions without giving them a name. It's called the lambda notation. How many of you have heard of it before? 1, 2, more? Cool. So this is going to be the hardest part of today, but we better get it out of the way early. So if I want to define a function, a squaring function, I can say lambda x times x. Okay. So this is as you can see, there's no error, right? So this is something that the interpreter Python understands, and then we can directly apply this function to a number, and we're going to get the result. All right. So this is a function, and we didn't bother to give it a name. And by introducing this notation, essentially numbers, strings, functions are on the same footing. Okay. Now, when that is possible, all right, I can have functions that take other functions as arguments. So for instance, this looks like x times x, but this operator star, what if I don't want to say what it should be from the very beginning? So instead of star, I could have either plus or star. I don't want to say what it should be. I know that I want to use a binary function, binary operator, to apply it to x twice, right? So whatever circle plus operator I have there, I want to say I have x circle plus x, right? But the circle plus, I don't want to say it up front. So I can create a function. I'm going to call it twice. And it takes an argument, which should be a function, and it takes another argument x, which is the same x as before. And I want to return, so because we use a def, we have to use a return. Whenever we have a lambda, we don't have to use return. And I'm going to use f applied to x and x. So now the first argument could be something like lambda x times x. This would be multiplication applied to 10. And we're going to get, do I need brackets here? Oh, sorry, I forgot about the, I shouldn't use def. So twice, lambda x times x, 10. And so what happened was that with the error that I typed in, I redefined. Okay, yeah, I'm sorry. So twice x and y, right? So this is multiplication, x times y, applied to 100, and this will produce 10,000, right? 100 times 100. However, if I take this, the very same function, and say I say plus here, I would get 200, right? Which is 100 plus 100. If, for instance, I go and say x times x plus y times y, I'm going to make this 5. I don't want a number that is very large. I'm going to get 50, right? So what does this do? Well, if you look at the definition, which is here, this was the definition, right? So, not this one. This one, right? It takes an f. This is the f. And it applies twice. This f takes 2 arguments, right? And it applies f to x twice, right? And now this f, I don't have to say it up front, what it is. I can say what it is later, right? And because I have the Labna notation, I have the ability to provide functions that are arguments, okay? So since I have such an ability, one interesting thing would be to write a function that solves arbitrary equations, all right? So in general, how do we specify equations? Equations most often are specified as a function being equal to, say, 0, right? So I have equations of the type, right, fx equals 0. For instance, if my f is x squared minus 2, x squared minus 2 equals 0 would have a root that is equal to the square root of 2, for instance, right? How could we solve an arbitrary equation? Well, there's a method called the bisection method. So I would guess an interval where the solution might reside, and I will check the sign of the function at the ends of this interval, right? So I will take the value. So let's say the interval is AB, right? A is the smaller value, B is the larger value, and I have my equation being fx equals 0, right? So I compute fa, I compute fb. If their multiplication is negative, it means that one is positive, one is negative. I don't care which is negative and which is positive. One is definitely positive, one is definitely negative. There's a root in the middle. So I'm going to go to the middle of a and b. A plus b divided by 2 is going to be the middle. And I'm going to see, is my root between a and the middle, or is it between the middle and b? So I'm going to check fa compared to f of the middle. If they have opposite signs, the root is between a and the middle. On the other hand, if f middle times fb is negative, I'm going to have the root in between middle and b. So I'm going to switch the interval of interest from a and b to either a and middle or middle and b, depending on where I find that the root should be. And I'm going to keep halving till the interval is so small that it is within my margin of error. Okay? And notice how I'm not saying what f should be. I'm not saying upfront what f should be. Whatever f is, if I have a decent guess of an interval where the solution should reside, by performing this bisection method, I should find the solution. Okay, so let's try to define the bisection method. Okay, so def bisect. All right, we're going to take a function f, which is an arbitrary function. We want to solve the equation fx equals 0. And we're going to take a and b as our guesses for an interval where the solution might reside. So we're going to say return, all right? And this is going to be a multi-line answer. So whenever we want to write an expression on multiple lines, we have to end with backslash. So I'm going to put a backslash here, and we're going to have the same kind of pattern, right? Something, if something else, if some logical condition, else something else, right? So the middle is a plus b divided by 2. All right. So what do I want to return, right? If a and b is less than the margin of error, right? So if a and b is less than margin of error, I can return f applied to a plus b divided by 2, right? If and I'm going to always assume that a is smaller than b, so b minus a is less than 0.00001, let's say. Okay, and I'm going to let's put the else here, else, and I'm going to add a backslash, and otherwise. Right? So if I have reached a point where b and a are very close, then that's going to be the result. Right? So if so I'm going to have something if something else, right? Else, and then I'm going to put a backslash here, right? So let's see. So if f a times f of a plus b divided by 2 is less than 0, right? That means that I should have a root between a and a plus b divided by 2. So then what should I have here? Right? So think of it as a function, right? So bisect of FAB is equal to bisect of FA and a plus b divided by 2 if it's likely that I have, it doesn't matter how far or close the right limit of the interval is, right? So what does this mean? That instead of starting from b, it's as if I'm starting from a plus b divided by 2. But it's the same thing because it shouldn't matter as long as f times a and f of the right side limit is negative, then I have a very good chance that, I mean, the solution should be there. All right, else. So what else is there? And actually, I don't need. Okay? Is there any other case? So I have to keep saying else all the time, right? If I say if, I have to say else. So what do I write here? What case is left? All right, so one possibility of getting a result is this. Well, I'm hoping you understand. I'm completely unable to do so. I think because the font is so big, I have increased the font so large to such a large size that. So this is one possibility of getting a result, right? There's no mention of bisect here. So this will just return a result, right? So or I get a recursive call, or I get another recursive call. But if we look at all the possibilities, there's one that is left here, right? So fa times this can be less than 0. Fa plus b times f of fb can be less than 0, right? Or both of them are 0, right? The chance of that is very small. But we still have to assume that it is. So in that case, if both of them are 0, the likelihood is that a plus b divided by 2 produces the root. We have hit the root just by accident on the second one. So we're going to return yet again a plus b divided by 2. Okay? And this is the bisection function, right? So now let's see if we can find out the square root of 2. So I'm going to do bisect of, so the function whose root would be square root of 2 is lambda x times x minus 2. And we're guessing that there's a root between 0 and 10. Okay, and let's see if we get a result. Oh, we don't want f. We want a plus b divided by 2. So sorry. So let me try to select this. What we want is not f, but we want a plus b divided by 2. And the same here. Okay, and let's repeat bisect. All right, so we get this value, right? And then SQRT2, and we can see that they have 6 decimal places correct, right? Which is exactly how many decimal places this margin of error here has, right? This one has 6 decimal places. And, right, we have obtained a result that is correct up to the 6th decimal place. Right? If you make this number even smaller, you're going to get higher precision, but it's going to take longer to get there. Now, this length of time is hard to notice, hard to measure. That's just milliseconds. But when you do it on many numbers, they add up, and then it can add up to hours and hours. Okay? If you want to compute the cube, or the square root of 3, right? If you want to compute the square root of 3, you can just put 3 here, right? And we're going to get the square root of 3, and we can compare the result. Okay, and we see again that we have about 6 decimal places that are identical. I mean, neither of the results is correct, right? Both of them are approximate. But the one that comes from the standard library, which is this one, is surely has better precision, and it is computed faster, right? Because we can't get a very good computation in the first programming class, right? How about the cube of 2 or the cube of 10, right? So we can go here, and the cube of 10, we would have a root of the equation x times x minus 10, right? And we're guessing that, 10, 10 to the cube is 1000, so there's surely a root in there. And if we run this, we're going to get this as the cube of 10. And actually, there is a power operator. We have a power operator, which I think is it star star? Yes. So 3 star star. So I want to say what is the 3 star star 1 divided by 3. 1 divided by 3. And we see the expression again. We see that about 6 decimal places are correct. Right? How about exponential effects which is the one that doesn't have an analytical solution at all? So let's say sine x equals x divided by 2, right? So from math import sine, and then we want sine x minus x divided by 2. Oh, at 5? Seriously? It's very strange. Cannot. Sine x. Okay, so so there has to be an error there. I'm going to guess a solution between 0 and 4. All right, so what happens here is, this is a very interesting case. I never tried it. Because of errors, right? It's neither the case that this is less than 0, neither the case that this one is less than 0. I know why. Because sine is a non-monotonic function. That's why. So sine will have multiple roots, right? That's the reason. So we have to select an interval for which sine is sine is monotonic, which is up to pi divided by 2. So let's go to pi divided, I think it's pi divided by 2. Okay, so it's actually called pi non-capitalized. So this should be pi divided by 2. And now we get a correct result, right? So just to convince you that online. So right? So it has a root here. Control command plus, right? So this function has a root right here, and we can actually find out if we don't want to plot. So the other thing that is interesting to do is see plot x and x divided by 2, both of them, sine x, right? So you see x divided by 2 goes like this, and then the sine goes like this, and they have a root right here, right? So this is the root that I want to find. And obviously this root doesn't have an analytical solution, right? You can only solve it numerically. If I don't want to plot it, I think I can say equals solve. And it seems that we're not that close, right? So there's 2 solutions, but this one seems to be 189, and what we got is, where are we? Oh, it's here, 0.785. I wonder why. Oh well, we can only do so well. Will be interesting to understand why. It seems like.
So when I change the upper bound to 2, it actually gives the correct result.
Oh, because this is actually pi divided by 2, I think. But if you change it to 2, then you're. So if you're saying 2 here, it gets the right result. Okay. Well, it will be interesting to find out why the result is incorrect, right? So we're going to see later that actually this function can be hardened. So there are some cracks into this code in its current form. Right? But because I don't want to make things too difficult, right? In the first class, I have left a little bit of a gap here, and probably this function falls into that gap, and you get the wrong result. We get the wrong result, right? So we're going to write this soon once we move away from recursive functions, and then we're going to fix those gaps, and we're going to rerun these codes, and we're going to see the correct results. Okay, cool. So this is it for today. Questions? Yes, if not, class dismissed. See you next time.